Welcome back to our deep dive on RF propagation. Today, we're going to do things a little differently. We're not just technicians, we're detectives. And our environment? Well, that's our prime suspect. The path our signal takes is the crime scene, and it's our job to figure out who's behind every last lost packet and every single faded signal.
All right, detectives, before we get our boots on the ground, let's take a quick look at the case file. So, this is part 14 of our 20-part series, and it's all based on some incredibly detailed field reports from the RFI detectives. They're a part of Virtualization Options, LLC. We're going to be building on everything we've learned so far to really crack this case.
You know, as anyone who spent time in the field knows, a signal's journey from point A to point B is, well, it's rarely a straight line, right? We're going to treat that propagation path as our primary crime scene. It's full of clues, all sorts of misdirections, and plenty of hidden actors.
And here's the crucial point. It's right here in the definition. See the antennas? We know those. The equipment? We can test that. But the environment itself, the medium our signal has to fight its way through, that is the most dynamic, complex, and challenging variable we face every single day.
I want you to think of this list as our usual suspects. On any given path, a signal has to run this gauntlet. We've got reflection, the bounce, refraction, that's the bend, and diffraction, which is the wave's sneaky ability to creep around corners. Each one of these has a totally unique signature, and your job, as the detective, is to know which culprit is tampering with your evidence, and your evidence is the signal. Okay, now I want you to look up way, way up. Our first major adversary, and believe it or not, sometimes our greatest ally, is a variable system parameter that's a cool 150 million kilometers away. We're talking about the sun. And this statement from the source material, this isn't just some theory from a textbook. It's an operational imperative. For anyone working with high-frequency systems, the sun isn't just a backdrop. It's a very active component of your network that can and will bring it down in minutes if you're not paying attention.
So here's how it works. This isn't random. The single most important variable in long-distance radio probably isn't your equipment. It's the time of day. And that's because the sun literally builds up your communication path every single morning and then tears it down every night. This constant energizing and de-energizing of the ionosphere is the #1 reason why your usable frequencies and your link quality can change so dramatically from noon to midnight.
And this chart, wow, this just illustrates the evidence perfectly. Just look at the data. For a pretty typical HF path, the maximum usable frequency, the MUF, can vary by a factor of 4 or even more throughout a single day. That massive peak you see around noon, that's not a coincidence. It's a direct result of solar radiation doing its thing. And that trough right before dawn, that's what happens when it's gone.
All right, let's bring our investigation a little closer to home. Let's see how the physical terrain itself obstructs and messes with our signals. I'm talking about the obstacles you can actually see, you can walk, and you can map out.
Now here, we're looking at two very different crime scenes. Over on the left, you've got a single, large-scale obstruction, a mountain, and it's creating a fairly predictable shadow. But on the right? Well, on the right, we have the total chaos of the urban canyon, where that signal becomes a ricocheting bullet, just bouncing off of every single surface.
So what's really fascinating about this comparison is how it breaks down the two main types of terrestrial challenges we face. One is about overcoming a single massive obstacle, which often means using repeaters. The other is about engineering for 1,000 smaller ones, which demands really careful antenna placement and smart system design to handle all those complex reflections.
So we're faced with these powerful foes, right? Both cosmic and terrestrial. How do we systematically troubleshoot? We don't guess. We absolutely do not guess. We use a detective's framework to isolate the real cause. And here it is. This is the playbook. And your first step every single time should be to eliminate the obvious. Before you ever blame propagation, you've got to verify your power output, check your SWR, walk your cable runs. Seriously, don't waste hours analyzing the ionosphere when the real problem is just a loose connector. This is one of your key diagnostic questions. When you start analyzing the patterns, does the problem seem to appear and disappear with the sun? If that issue consistently follows a diurnal cycle, a daily pattern, your prime suspect is almost always the ionosphere. It's the big clue that tells you to stop looking at the ground and start looking toward the sky. And really, this is what it all comes down to. This is the core mission. The environment isn't some static problem that you just solve once and you're done. It's a dynamic, living system that we have to understand, monitor, and adapt to. The best RF detectives out there know their physics, for sure, but they also know how to read the signs and be ready for whatever the path decides to throw at them. So the real question isn't just what broke, it's what changed.